Okay, good afternoon, everyone. So today we're gonna continue, most likely finish our yield editor exercise in R. I guess maybe before I do that, before I get started, does anyone have any questions or any thoughts from previous class or maybe about the assignment or the mini project?
Yes. I have a question about the mini project. I was looking to the questions, and there are two that seems to be the same. Like that, at least for the yield data, because one needs to summarize the overall county average of the yield, but there was one before that was still plotting plotting the yield for all the county in all the years. So I don't know how they are different.
Yeah, so I
Let
think
me.
for yield, I think that question may actually be the same answer. Um, I think that question makes a difference for other things like planted area, harvested area, production, because in one of the questions, I think the key is to take the average, and on the other
Mhm.
question, the key is to take the sum. And for yield, I mean,
This,
it doesn't make sense to take the sum, right?
okay.
Yeah, so I think that's what you're referring to.
Okay. So I will do the same plot. And
Yes,
that's it.
if you have yield as your category. Yep,
Okay.
awesome.
And also, like the assignment, I don't know if I use C, but I wasn't able to run it on my computer, and we couldn't figure out why.
Mm-hmm.
So I asked one of my classmates to run it on his, but it didn't turn out as I wish. But I did do what I could.
Yeah, so Neva was telling me earlier that she connected with you and that you're gonna try to run on somebody else's computer because I think you worked on Neva's computer, right? Or no? No?
Yes, it did. What in my computer?
Yeah, so we worked on hers, but not on yours, right, Benedetta? Yeah, I have not looked into the assignment responses yet, but I'll keep that in mind as I go through it. And I definitely don't want you to lose any points because of something technical. I mean, computer technical related. So I'll keep that in mind when I'm grading, and I may follow up with you if that seems like it was an issue.
Okay, thank you.
Right, thank you. Um, all right, so I think with that, let's resume our exercise that we started on Tuesday. As always, I want to ask you to open so go into the 07 Year Wonder folder and then launch in the R project icon. And that's how we're gonna get started again. Perhaps you already had the RStudio open on your side with that project, so we didn't have to reopen it, but at least that's what I'm doing on my side. And then for me, again, my environment is empty. That's what we want always when we open RStudio. We do not want to have those ghost objects from one session to the next. I'm going to go in the Files tab on the code and then just open that Yield17 editor partial right there. All right, so we stopped at determining those thresholds on the statistical distribution of yield. That's what we're gonna use to apply our first filter, which is the min and max yield. If you are on that chunk, you probably, and your environment is empty, which I hope it was, then it means you don't have anything else that we've done on next class, at least not running yet. So you can come here to the raw yield quantiles, on this chunk here, you can run all above by clicking on this button. That's gonna get everything else that we've done already, go through that. And it's gonna basically stop right at this chunk. And again, just as this is going through on my side and maybe going through on your side, a reminder is that for you to, if you have to install packages, never leave those install.packages active, right? Either delete them from a previous chunk or comment them off. So if you do have to do one of these run all chunks above, it's not going to reinstall a package you already have. All right, so for me, it went through nicely. I didn't leave any errors in my code, so it was able to run through until this chunk. I have all of my objects here on the right. Now we can basically come here and play this chunk that we already developed last class. If you remember, we were getting the low quantile as the 10th quantile of that yield distribution, basically this distribution right here. Then we're getting the upper quantile as the 99th quantile. We did the inner quantile range by doing the upper minus the lower quantile, and then extending those quantiles. So the low quantile extending it lower than the lower quantile, and the max quantile or the max Y extending above or beyond that upper quantile. And then we're going to use this min Y and min X to then be our guides of what data points we want to filter out, what data points we want to leave in the data set. I believe this is the point that we stopped. And now we're going to do something that I think is going to be useful for us to visualize our own data. But basically, what I want to do is to replicate the same figure of that paper. So if I just go back to that, paper, I just want to reproduce, let me get to it, this figure. So I want to have the statistical distribution of yield, our lower quantile, our upper quantile, our max Y and min Y. Basically reproduce this plot, but for our data. All right, so to do that, I left you already the beginning of the code. So we have our distribution of yield data right in front of us. Now what I want to do is just add some vertical lines that are going to be related to those quantities. So the low quantile and up quantile, and then the min Y and the max Y. So let's do that. The next thing that I want to do here on this plotting, we're going to be using a geom that's called geom vline for vertical line. So add a plus geom vline. I'm going to do the first one here without asking you for help, and then I want you to help me after that point. So we're not going to be using a data frame or the aesthetics here. It's going to be very straight to the point. So if you hit tab here, there is one argument for x-intercept. I basically just want to tell it what is the x-intercept value that's going to draw a vertical line on. So the first one I want to give is the low Q, so that lower quantile. The object name is low Q yield. If you just run this is what happens. Now, I do want to change a few things to help us identify what is what. So one of them is I want to change the color. So I want this to be red. So I'm going to say color equals red. Notice here, I know this can be a confusing point, but by now I hope you're already getting the gist of it. Because I'm changing color to a fixed color value, I'm giving that color value right here in the geom, and it's not inside AES. Right? In AES, it would be color equals and then a variable name or a column name and not a color name. If you run that, we get a red vertical line at the value of low Q. And then I want to change the line type as well. So add a comma, I want to say line type equals to 2. This is going to be a dash line. Okay, so now my goal is to add the same thing, but for the upper quantile, and I want that to be blue. So we can just recycle this code. You can just copy this geom, add a plus after it, break line, and paste it. Now, if I want to add the upper quantile and make it blue, we have to make some changes on this code here. but by now I hope you already got the idea of how to do that. So I want to ask for your help. Amandeep, what would you change here to plot the upper quantile and have that as blue? Okay, so x-intercept equals to UPQ yield, okay? And so if we run this, it's going to do that, right? But I want this to be blue.
Oh, yeah. Red.
So just change red for blue, right? Oops. All right, cool. So that's our lower and upper quantile that we just plotted there for us to visualize. Okay, so now the next thing is I want to add the values of min y and max y. Let's do min y first. So remember, min y is going to be more to the left than lower quantile, right? So if I come here, we can add a plus again, and if you can just paste again the same code. So I want min y to be still red, but we have to make some changes here on this code. So let me go online. Kiathi, what would you change here to plot min y?
Maybe the line type should be changed and the x-intercept should be min y.
Okay, so x-intercept would be min y, and then
Yeah.
we just do this, it's gonna be like that. So we don't know what is what. I like that you're already thinking we should change something. We could change the color, we could change line type. I think we can go ahead and change line type. So if you do line type equals 1, it's gonna be a solid line. Maybe we can do that. Close my email. All right, so now next step is I want to make the same idea, but for max y. So I'm just gonna copy this latest one that we did, add a plus, hit return, pasted, and then I'm gonna ask somebody in Tifton. Let's see, is Marco there?
Yes.
Marco, what would you change here for our next step to plot max y with a blue solid line?
I change color equals blue
Okay.
and type equals 1, the same.
Okay, so line type 1, but what about x-intercepts?
That is max y.
Max y, right? Perfect. All right, so this is how that will look like for our data. We basically made the same plot as on that paper. Now, let me ask you all first, and then I'll call one of you after that. If you could use words to tell me between the line color whatever and line type whatever. So let's say you could say between the line options are blue or red, and then the line type would be full solid or dash line. Those are the values that we are going to keep. So, because some values here we're gonna remove because we're considering they're erroneous, and some values we're gonna keep. So I'm asking you to tell me in words between which lines are the values of yield that we're going to keep in the data set. So look into that. Take a quick second here to think about it. And let me ask somebody in Tifton. So let me ask Polly, what do you think?
I think we could keep the values for the low quantile and the upper quantile.
So they're gonna keep the values in between
Yes.
two lines?
Yes, I think we could keep the lines. Wait, no. We can keep the line between the solid line. That would be the minimum and the maximum.
Yes. So we're gonna keep the values in between the solid red line and the solid blue line. Another way of thinking of this is we're going to remove out any value that is beyond the blue solid line or below the solid red line. Those values are going to be removed from the data sets. I just want to show you here one way that we could visualize that, which is, I think it's a really neat way of thinking of this. So add a plus there. Now we're going to use a geom that is actually, it's kind of like a geom, but it doesn't start with geom. It's the function is called annotate from the ggplot2. We need to say that the type of geom we want to annotate with is equals to rect for rectangle. And then we need to tell here what are the boundaries of this rectangle. And basically what I'm trying to do is have a rectangle here that represents the values that we're going to keep. So on this annotate here, it has the following arguments: y min, y max, x min, x max. Those are the coordinates on the y and x axis that we want that rectangle to be within. So that's kind of built here, and I know this goes beyond just, I guess, statistical thinking, but more about maybe logic. If I want to give this the value on the y-axis, that is going to be the minimum value on the y-axis where this rectangle starts. So imagine a rectangle here, and we're going to give the coordinates for the corners of this rectangle. So y min is basically the lower side here. So this boundary of the rectangle, right? So we have a rectangle like this. This is y min. So what would be the value that you put on y min if I want to have a rectangle like this? So if you think of a rectangle like this, y minimum is this value, is the minimum on the y-axis. So what would be the value there?
What about x equal to 0?
Yes, y equals to 0. That's a good guess. Thanks, Polly. All right, so thinking still on this, so we just said the minimum is here on the y equals 0. What about y max? What is that upper boundary of this rectangle that we want to, on the y-axis? What value would you use there? Luke, what do you think?
You could just use 0.00125 here.
Yes, okay, that's a great guess, and that's what I was expecting for anyone to say. Another way of thinking of that is if you don't know exactly what is that number, you just want it to cover the entire upper boundary, is you can just say uppercase I inf for infinity. So it's basically going to infinity, and you don't have to worry about knowing exactly what is that value right there. But yes, that would be a great way of thinking about this, Luke. So that you're thinking the right direction. All right, so we cannot run yet because we still need to give x min and x max. So I guess we're just gonna go through x min and x max, and then we'll run and see how that looks like. Okay, so now let's give it x min. So x min, so x, now we're talking about this, x min and x max. What is this boundary, x min, that you would give it? So max y, I think, is this.
Yeah. Minimum y.
Minimum y, yeah. Yeah, now we're kind of talking about x and y and min y and all that, but yeah. So the x min would be our variable name called min y, which is this column here, right? And then finally, our x max is going to be what value? What do you think, Mohit? Is Mohit in Tifton today?
Yes.
What do you think, Mohit? So this is what we're talking about. Yes, go ahead.
Y max?
So the x max now, so x max is the argument of the function, and then we need to give it a value here, right? So what value do you think that would be?
Infinite?
Sorry, can you say that again?
So like 4,000?
No, so the value we're looking for is this one here. Remember, we're trying to create a rectangle between the values we want to keep.
Between 2000 and 3000.
But what is this value here? Let's see, Benedetta, what do you think?
It would be. I don't know. Can we say that it's the mean y?
So mean y
Right.
is this one here.
Yes.
What about this one? This is the one that we're trying to
Max y. Sorry.
max y. Yes, exactly. So that would be max y, which is a value that we calculated, right? So I know that is a little bit confusing because the arguments are called y min, y max, x min, x max, and then we calculated some variables that we assigned to the objects min y and min and max y. So it can be a little bit complicated and confusing, but I hope that you got the gist. All right, so now we can go ahead and run it. And that is exactly what we were looking for, I guess, even though it's not the most beautiful plots you've seen. So a few things we can change here to make it just a little bit nicer is to decrease the transparency. So we can say alpha is transparency, ranges from 0 to 1. Let's put 0.6. So 60% solid only. And if you wanted, you could give a different fill. So because we're keeping the values and keeping is good, let's have a fill of green just to illustrate that. So this is basically us showing in a plot what we're doing with our data and with the limits applied to our own data, right? So notice that upper and lower quantiles, and then mean y and max y were all calculated based on our data, which we did up here. So these values that we found are data specific. If you change data sets, these values have to be recalculated. All right, so we're basically keeping only the values that are shaded in green. So all the data points between or within this green rectangle is what we're keeping. So that is just visual, right? We have not done anything to the data yet. That was just us getting those thresholds and then plotting them. So now the goal of the next chunk is to actually apply this filter to our data. If you go to the next chunk, I'm calling that EO17WYF for yield filter. That's why I named it this way. Let's give it the assignment symbol. As always, we're going to start with our incoming data set, that is yield17_W. And again, my goal on this chunk is to keep only those values within the green rectangle. How would you do that? Let's begin step by step. What function would you use for that? Okay, I'm going to set filter. I agree. Or select. Okay, select is for columns, right? Remember that. Filter is for rows. We're filtering rows. Perfect. All right. So now, and here again, I want you to realize that we are thinking about what we're doing and then implementing in code. So in plain English, what I want to do is keep the EO values that are in between min y and max y. Plain English, no art knowledge required to develop that thought. Now, the next step is how do we apply that thought and that step through coding? So if we go back to Tifton, let me ask Luke. What do you think, Luke? How would we write out that condition for filtering based on what we know of what are the limits that we have here and what variable we want to filter?
Could you just do like a logical thing where yield in pounds per acre is set greater or equal to min y and less than or equal to max y?
Perfect. You nailed it. Let's do it then. So the column we want to use here is yield in pounds per acre, right? That is the one that we used to up here on the, when we're determining the thresholds. So you cannot do here on the threshold determining pounds per acre, and then on our filtering use kilograms per hectare, right? It's not gonna work. You have to keep the same variable. So Luke was saying if yield is equal to or greater than which value? Which object?
Min Y.
Min y, right? Yes, so if yield is greater than here, and we have to have an and here, because if you just keep it like that, it's gonna filter everything greater than min y, meaning including this tail, and we don't want that. We want to cut out any values after max y. So we have to have an and here to say that both conditions need to be met for a value to remain in the data set. So yield pound per acre equals to or greater than min y, and yield pound per acre equal to or less than max y. Oops, let's see. I think maybe, let me see what is going on here. Maybe it has to be this order. Let's try that. Okay, I think it did not work, probably because my equal sign is not in the right place. Yeah, okay. Yeah, so I think on my side it didn't work, and if you were copying along, yours wouldn't either. Because when you have greater than or equal to, the equal sign comes in the second position of the Boolean operator there. I had put in the first place or the first position, and it was giving me an error. So just make sure you have your equal sign on the second position of the Boolean operator. So meaning greater than or equal to, and less than or equal to. All right, so if you run that, it should run all right. If you print it now, our object now has 30,385 rows. I just want to print yield17W again, just so we see how many rows that starting data frame had. So the starting data frame had 31,724. So we removed about, more than 1,000 observations. Almost 1,500 observations were left behind because they fell outside of this range. All right, so now that we at least applied these two filters, notice we applied two filters, right? The mean yield and the max yield. Let's just get a summary of this new object. So the new object is called yield17WYF. So if we just run a summary there, now notice that our yield values are ranging from 229 to 2,558. Before, when it was just yield17W, so before filtering, the minimum was 0 and the maximum was 4,000 something. So we already know, I mean, we would expect to see this effect because we applied a filter, but we are just checking that on the summary and it matches what we were expecting. Okay, so now we're gonna do the same thing on speed. If you remember, speed was another variable that was used in that paper to filter yield data points. So we're gonna use speed now. I left you here the code for to look at the raw distribution of statistical distribution of speed using geom density. You have already seen this plot. But now we're going to determine all those metrics for the lower quantile, upper quantile, inner quantile range, min y, max y, but for speed instead of yield. If we just take a look here at the raw speed summary, so we can compare later, minimum is 1, maximum is 5. All right, so I left you part of the code here, but we still need to code along the low Q and the up Q speed. The reason why I did not leave you the code already for this is because if you go back to the paper, you're going to realize that the quantiles that were used for yield are different from the ones used for speed. And so I want us to be aware of that change when we're coding. So if you're gonna come on low Q speed, we're gonna use the function quantile. We're gonna give the data frame name. It's gonna be yield 17. So I have here actually, I have yield 17W on my cheat sheet. But maybe we should already use the clean one. So let's do that. Let's deviate a little bit from what I had originally. So EO17W YF, which is the one that has already been filtered out for the yield data points. And then $ speed miles per hour. And then the quantile that they used for speed on that paper was the 8th quantile. So to specify that, we say 0.08. That's the 8th quantile. If you run that and you print it, that is 4.6. That's the speed where the 8th quantile is. Although, you know what? So this plot that I showed you above is with the fully raw data without removing the yield filter first. So maybe let's just keep, I think that, one could argue to use the completely raw one or the already filtered version. So maybe let's just keep the full raw because I think that's going to give us a better idea. So EO17W $speed. And then if you run that, this is going to be 4.6. So it's a little bit lower than using the already filtered for yield version. All right, now with the UPQ speed, the same idea, right? We're going to use the quantile function on yield 17_W $speed. And here the probability that the papers proposed was still 0.99. So the 99th quantile. So if we run that and you print, that is 4.8. So notice how it's very tight, right? So meaning that you have only, so you basically, if you had, in this distribution, what the quantile is doing is basically taking this value here, the first value as 1 and the last value as the 100%. So the 8th quantile is somewhere really close to here, saying that there's really, the 8th quantile on this distribution is basically 4.6. So it's here. And we don't see that too well because they are all behind each other, right? So maybe like at 4.0, for example, there may be 3,000 points with that speed, or maybe more, right? So there's a lot of points that are just stacked here. We cannot really see them. But for us to get an idea, the 8% of that data set is going to be at 4.6. So really a very high concentration of points, really close to 4.6, or after 4.6 in that sense. So not a lot of points below it. That's what I'm trying to say. Then let's calculate our inner quantile range, IQR. That value is 0.2 because it's the difference between our upper quantile of 4.8 and our lower quantile of 4.6. Then we extend again that lower quantile downwards and upper quantile upwards using the mean. In this case, I'm calling mean V because it's for velocity or speed, and max V for the same purpose. So our mean V here is going to be 4.564. Notice that it just retrieved a little bit. It was not as dramatic as with the yield data. And then our max V is going to be 4.836. So the same way, it did not go too far out, just a little bit. And again, the reason why this interval is shorter is because of the data distribution itself, right? The data distribution of speed is just a lot tighter. There's like 99% of the points are in that very narrow range between 4.6 and 4.8. Whereas with yield, it was more variable, the distribution of the data. All right, so I basically left all the code below to create the same lines. The only difference is that now they're all for speed. So if you just run that, this is basically what that looks like. We're just keeping the values within that narrow window that is colored green. That's all. We're moving everything else outside of that window. So now if we come to our filtering min, max, raw speed, I do want to, in this case now, because we are applying consecutive filters, I do want to bring in, starting off with our already filtered data frame for yield. So if you give the assignment symbol, that is going to be yield 17 WYF. So we basically calculated here the boundaries that we're keeping on the raw data, but we're applying those filters on the version that has already been filtered for yield min max. So we do this. Well, we're going to use the filter function again, but let me ask somebody else. Kiathi, what would you code here? Let me just print EO17 WYF so you can see the variable names.
Speed miles per hour.
Okay, so speed miles per hour.
Give me a second. So that should be yeah, that should be speed miles per hour greater than equal to minimum speed and speed miles per hour less than equal to maximum speed.
Okay, so let's implement that. So it's speed miles per hour greater than equals to, what is the name of the object?
Min v.
Min v, right. And then speed miles per hour less than equals to
Max v.
Perfect. All right, thank you. Now, if we run that and we printed, notice that now we have 28,950 data points left. So we filtered out about 2,000 we filtered out about 2,000 rows at this level. All right, and then let's just get a quick summary here, just to check again on that data distribution as a table. So I want to get the summary of yield 17 WSF, which is SF in this case is just to say that it was the speed filter. There's nothing to do with SF object, which in fact this is an SF object, but that's not why it's named SF. And then $, oops, $ speed. So now, as we were anticipating, it's ranging from 4.6 to 4.8, as those were within the values of our threshold. All right. Now, the next step here is going to be for us to apply our fifth and last filter of this exercise, which is going to be the position filter. As you probably, as you read on the paper, because you had an assignment, so you had to read the paper. But as you may remember, the position filter, there are two ways of doing this. One would be to extract the X and Y coordinates and do the same exercises as we just did with the X and Y coordinates. That's one of the ways, is to use the coordinates and then apply a statistical approach to that. While we could do that, I think that the better way of doing this is just by bringing our boundary, right? Because our boundary is really what's going to dictate where is our field. And if you remember from the paper, this filter here is helpful in case, let's say sometimes the operator may turn on or is going to turn on the equipment, the combine or the picker in the shop, and then he's going to drive to the field. So sometimes you're going to have some data points that are just the path to the field that have nothing to do with actual yield data, but you still have yield data points for all that path. Or another reason why this could be important is perhaps that combine is going through the field and then it loses GPS quality, it loses access to, or it loses the signal from some of the satellites, and the precision just falls dramatically. And maybe you have a drift where maybe it's harvesting the field, but then one data point is way out of the field because of that GPS signal quality. So these points we want to remove. So any point that is not within your field, we want to get rid of them. So for that, we're going to use our boundary instead of using the statistical approach that we've done for speed and yield. So let's bring our boundary here. Let's see, our boundary is in our 05 digitizing project. So we need to get there first. But before we navigate that, what function do I need here? What do you think, Pauline? Any thoughts, Pauline?
Read s.s/sf
So read
/sf.
underscore SF, right?
Yes.
Perfect. So let's bring here our quotation marks. We need to navigate out a few folders, right? So .. if you hit tab, you are inside of your EO Monitor project. We need to get outside of that and go and be able to see the 05 digitizing folder. So another set of .. Now we're seeing all of the projects. Let's go inside 05 digitizing, go inside output, and we have our boundary.geojson right there. So that's what we're bringing back here. So if we run that and you print it, well, it is our object, it is WGS84. And we can just do a very quick map view just to make sure it is the correct boundary, right? It is the correct shape. So let's do a map view of the boundary just to double check very quickly we have the correct object. All right, we do. It is in the right place. It looks like what it's supposed to look, so we're good. Okay, so before we do actually implement the filter based on the boundary, we're gonna be doing something here. So a lot of times, as we saw, some of the issues and something that you answered on the quiz, some of the issues that we have with yield data near the boundary is here on this case, on the headlands is where we're making, or the operator is making the maneuver to get from one row to end at the end of one row and then finding the other row. So that coming out of the field and coming back into the field has some problems with that because you have partially filled header. So we don't have a lot of cotton coming through yet. Also on the sides, we have issues because if you're harvesting maybe like half of, like your picker, only half of the header has rows because the other is already at the end of the field. There's nothing after that. So we have partially filled headers at the east and west boundaries as well. So what I want to do is to create a negative buffer. So to bring our boundary inwards a little bit. So we remove that outline, those points really close to the boundary because they probably have some errors in them. Now, because we are doing a buffer, which is a distance-based operation, it's better to do that with a boundary that is projected and not just a geographic CRS. If we print boundary here, and we check on the first panel, it is WGS84. This is a geographic CRS. That is not great if we are doing distance-based operations like buffering. So let's change that. I want to do that in this next chunk. So let's give this the assignment symbol. We're starting with boundary, give it a pipe, and then what? What is the function that we need here to transform this CRS from geographic to projected. What do you think, Mohit?
Transfer or trans?
Sorry, can you repeat that? Let's see, Benedetta, what do you think?
Maybe some like star from the star package transform.
Yes, so it's gonna be a function from the SF package because it is an SF object. But I think both stars and SF have a very similarly named function that is gonna be ST underscore transform. So we did this in the previous exercise as well, where we basically had to first set the CRS with a different function and then transform that from WGS84 to UTM. Yeah, so ST transform is when it already has a CRS, so boundary already has a CRS, it is WGS84. We just want to change that to projected. So here on the CRS, the one that we want to use is 6345. That's the EPSG code for the one that we need here in Georgia, zone 16 north. If you run that and then you print it, this is our object. Right, so now we have a projected CRS UTM zone 16 north. Okay, so what I want to do next is, if you remember in the beginning of this script, we created this object EOMap raw. If you just run that, it's gonna be that EOMap raw, right? So now because this is a ggplot object, or it's a ggplot that we assign to an object, then this object here is also a ggplot. Meaning that we can just come here, add a plus, and keep adding geoms if we want. So my goal here now is to just add the boundary so we can visualize it. Which geom do we need here if I want to plot this boundary along a ggplot? Amandeep, what do you think? GeomSF, right? Yes, so GeomSF, because the boundary is an SF object. So we're just gonna say data equals boundary W. And I just want to say fill equals NA so we can see through it and it does not block the yield data. Let's see. It is very thin. So maybe let me just increase the line. Let's see, maybe the line, I think it's line size or line width, perhaps. Let's try line width equals 1. Okay, that increased a little bit. We can see a little bit better at the boundary. All right, so we can see here that there are some points really close to the boundary. Some of them are even outside the boundary. Of course, that has to do with the fact that each one of us digitized this boundary individually. So it's going to be a little bit different, and that's okay. All right, so now I want to create, as I was telling you, a negative buffer. So I don't want just to apply this boundary because there are some points really close to the boundary that I want to remove. And those points are inside of the boundary. So I'll need to create a negative buffer to then apply that filter. So let's go to this next chunk here. We're going to create a buffer. And this,
Dr. Bastos,
yes.
sorry, I missed the code. Can you please go back to the previous?
Yeah, so now, so if you think of it, a buffer can be both positive, so going outwards, or negative, coming inwards. We want to do a negative buffer to decrease the area that we're keeping the values. So if you come here in the chunk buffer, we're gonna give the assignment symbol. We're gonna start off with boundary W. It has to be boundary W because it has already been projected. Let's give the pipe, and there is a function called st underscore buffer. Now this function here, basically we just it has an argument for distance. Because we want to do a negative buffer to come inside, it has to be a negative value. Maybe let's try -20, just to start off. If you run that, and if you print buffer, it is still just an SF object. It is of type polygon. It did not change anything about the actual object, except for that now it is a little bit shrunk. So now let's go back or let's go to the next chunk. And well, if you run it, we have ELRA, we have the boundary. Let me change the line width again to 1 so we can see better. So we have our boundary, and now I want to add a plus and add the buffer as well, so we can visually assess what points are going to be left in and what points are going to be removed. So if you add a plus here, let's add another geomsf, because it's going to be for the boundary. We just say data equals buffer. That's the object that we created above here, buffer. I want to also have a fill equals NA. Also want to change line width to 1. And then I want to give it a different color. I want to have this color equals to orange so we can see differently. Now, if you run this, this is what you see. Notice that now the new boundary or the buffered boundary is coming inside. It shrunk a little bit based on the original buffer, or sorry, based on the original boundary. So now if we use this the orange outline, so the buffer area, to clip out or to only keep the points inside of it, then we're basically removing all the points that are in between the orange and the outer boundary. Those points are going to be left out. All right, so if let's actually apply that on the next chunk here. So I'm calling this yield17 WPF for position filter. Give it the assignment symbol. We're going to start off with yield17. So I want to use here yield17 WSF, which is the one that has already been filtered for yield, for speed, and now is going to be filtered for position as well. Now, something interesting. The way that we did, the approach that we took, we're not going to be able to use the function filter, because we don't know what are the specific long, or in this case here, UTM meter coordinates that we would have to provide, right? And it wouldn't really make a lot of sense because there's going to be a lot of different coordinates. So filter is out of the question. However, we're going to use the fact that the boundary and the yield data points are SF. Both of them are vector geospatial data types. When you're trying to basically do a cookie cutter, we've done this in the past. We've used this function already. So let me see if somebody can remember. What was the function that we used as a cookie cutter in the past? Which is what we need to do. Sorry, can you say that again?
Intersect.
Yes, intersection. So ST underscore intersection. So there is an intersects and there's an intersection. And even though both of them are from the SF package, but they operate differently. The one that we want is intersection. So cookie cutter, think of ST intersection. And then here we just give the buffer object, which is the one that we want to. So we're basically saying take the buffer cookie cutter and cut the yield WSF with that. So if you run this and you print it, notice that now we have 26,480 data points. So we lost about another 2,000 points that were near the boundary compared to the previous, to the incoming object, right? So the incoming object that had already been filtered for yield and speed had about 28,950, and now this the one that we applied, the position filter has about 2,000, 2,500 last data points. Those were left out because they were outside of the buffer area. All right. Now, if you come to the next chunk here, what I want to do is, yes, we have a question? Sorry, if you said something I didn't hear. Nope. All right. So now, before we were doing the yield filter and we checked the summary of yield. We did the speed filter and we checked the summary of speed. There's no way we can check the summary of position, right? Because that is just coordinates. I mean, we could, I guess, but I don't think it would make a lot of sense. So what I want to do here is to actually check the summary of the yield column after we apply the position filter. That's my goal. So if you run that, you're going to see now that yield is ranging from 204 to 2,269, which I think is actually pretty similar to the summary that we did on the yield filter. Let me go back to that. Let me just write here so I remember on my outline here. So I'm going to go back on my outline and look for the min-max filter. So here, after doing the position, well, after doing yield, speed, and position, our yield data is ranging from 204 to 2,269. I want to check just yield editor here. So we had yield, 204 to 282. So the mean and max did not change as much, but I'm sure that the mean and the median did. So if you were to compare the median and mean between the filter that we just applied, the yield filter, with the position that had everything else, the mean and the median are going to be different. Slightly different, maybe not a huge difference, but a little bit different. All right. The next thing now is I want to create a summary of the raw yield data and the clean one. Yes.
I have a question. And since we all created random boundaries, are we all supposed to have the same data? Because for me, the maximum is not the same as the one you got.
That's a great question, Paulie. Yeah, so due to the fact that we all have slightly different boundaries, we're going to have difference in the results, right? And just a heads up, you're going to have an assignment in relation to this exercise coming up. And really, when you submit your answers, I'm not going to be looking for like hard numbers, because it's not going to be, because our differences in boundary. But of course, you still want to be within, some belt, I don't know, within 10 or 20 pounds of my answer, because I wouldn't expect to change too much, but it's not going to be exactly the same as mine. Yeah, but that's a great question. So if the numbers you're seeing on my side are probably slightly different on yours, but it shouldn't be drastically different. If it's drastically different, then something else is probably going on. All right. So next thing I want to do here is to basically create a summary table with the statistical distribution information about both the raw data and the clean data that went through five filters. So to do that here, let's see, let me tell you what I want to do more specifically, and then I'll ask for your help. I want to calculate the number of rows or the number of observations, the minimum value, the mean, the max, the standard deviation, and the coefficient of variation of the entire yield data, both on the raw and on the clean version. Let's start thinking about the raw first. So if we come here to the summary raw, the object that we're going to use is the yield 17 _W. This is the completely raw version, right? That had almost 32,000 observations. So I want to extract all of these statistical summary values from yield pound per acre column. What function do I need here? Okay, so I'm on DeepSet summary. So we actually need a function called summarize, right? So it's a little bit of a different name, but yeah, that's the idea. So we need summarize. If you remember, we used the function summarize before when we wanted to extract some statistical summary, like the mean of groups. And so normally the function summarize comes in a pair. It comes with a group by first. In our case, I don't want to have a group by because I don't want to extract the mean, for example, for any specific group in this data set. I just want one value, one mean for the entire column without any groups. So in this case, we do not need a group by. I just wanted you to remember that most of the time, summarize works with group by together. In our case, we don't have any groups that we want the summaries for, so we don't need to use the group by. All right, so let's begin here. The first thing I want to extract from this data set is the number of observations. I want to call this lowercase n. That is just the name of what I'm extracting. It's not a function. We're going to use the function called length. And then in here, I want to give the column of interest. For us, that's going to be yield pound per acre. So if I just run this and I print summary raw, I just have a column saying n and the number of rows. That's all it gives me, and it gives the geometry as well, but that is not relevant. Now, I wanted to extract the number of observations, but I want to extract a lot more other things. We can just come back here inside summarize, give it a comma, break line, and we're just gonna keep adding each metric that we want to extract. The next one that I want to extract is gonna be the minimum value. So we're gonna do min, I'm gonna call that min, and we're gonna use the function that is also called min for minimum, and give it the yield pound per acre column. If we run this and you print it, now we have another column saying min and what was the minimum value of that entire column right there. Next thing, I want to do the mean. So mean equals to, and then the function is called mean of yield pound per acre. If we run that and we print it, we get now the mean value. I also want to get the maximum value. I want to call that max. So max equals to, the function is also called max of yield pound per acre. If we run that and print it, now we have a max column in our output. I want to calculate the standard deviation. So I want to call that SD. There is a function called SD of yield pound per acre. If you run that, you get the column for SD. And then finally, I want the coefficient of variation, CV, equals 2. And here there's a trick, or not a trick, but a workaround. For some reason, R, and I think Python as well, do not have natively a function for CV. There's no CV function. With that, we're actually going to have to spell out the formula of CV and put that right here. CV is basically just your standard deviation divided by your mean. And then we multiply that by 100. So I want to open and close parentheses. And because we already created these objects before, so we have an object for mean, we have an object for SD, or not an object, but a column, we can just say SD divided by the mean times 100, so it's in a percent basis. So if you run that and you print it, we have all the metrics that we wanted. So basically our mean was of the raw data was 1,150 pounds of lint per acre with a CV of about 36%. Now, we're going to do the same thing for the filter data. And then at some point, we're going to merge both of them. because of that, I have to have a column that can help us to differentiate what data is raw, what data is summarized, is the clean data. So we're gonna give another pipe here after the summarize. I want to create, let's use mutate. I want to create a column called data, and I want that to have one value, which is just gonna say raw. So it's just a string saying that this data here is the raw one. If you run that and you print it, you come to the right. Now there is a column saying raw. And then I want to bring this column data with the value of raw to the first position of this data frame, because right now it's on the last position. There's a couple of different ways of doing that, but one of them is using a select. So let's use select. I first call the column data, and then I call a function that is called everything. So basically it's gonna put data on the first position and then bring everything else in the order that they are right now. So if we run that, you print it, we have data, and then n, min, mean, everything else right there. So this is our summary for the raw data. Let me take a look here. So we're going to 4:20 today. I think maybe we can take a quick break. I think this is a good point to take a break. 5-minute break, and then we'll come back and we'll finish this exercise here. And then yeah, I think that's probably going to be enough time to finish this. So let me give you 5 minutes here for you to take a quick break. And then we'll be back in 5. All right, 5 minutes have gone by, so let's resume our class. Okay, so we extracted all of these variables from our raw data. I want to do, and then assign that to an object called summary raw. I want to do the same now with our filter data, with a few differences. So one of them, or yeah, but maybe a few differences. One of them is we're going to assign to a different object. Of course, this is going to be called summary filtered. We need to change, so the 3 dots here are just a placeholder for us to think of what data set should we bring as the incoming data set. And then the third difference is that we're calling data equals clean. So this is something that we're specifying here. Okay, so what should be the object that we bring here? So delete the 3 dots. Now I want you to tell me what object should we bring right there. Marco, what do you think?
Sorry, we were muted. Yield PF.
PF, right? Which is the last one we did, the one that have been applied all 5 filters. So that is yield 17 WPF. Everything else is the same, so I'm leaving you the code. You don't have to code everything. Just run that and then print the summary filter. So all these numbers now are different, right? As we would expect, because we removed a lot of data points, and so a lot of these metrics changed. So I want to combine now both of these data sets so we can take a look in a table format, how they look like. So I'm just using the function bind rows, which does exactly what it says. It just takes a data frame and then another data frame and just binds on the row side. For this to work, for the function bind rows to work, you have to have the same columns, the same column names across both of the data sets, and that bind rows works. If you have different columns, different number of columns, different names of columns, then this does not work. So if we do that, then now we can see the first row here is for the raw data. The second one is for the clean data. All right, so, lots of things have changed. Let's see, I think CV is the last one we had. Yeah, okay, so we can just look at this. So just taking a look at this data, at this table here, what can somebody help me to interpret what you're seeing? It could be just one of the columns, it could be maybe more than just one, but how would you interpret what we're seeing right now?
Understanding the part, like the values you can see maximum
Mm-hmm.
in raw data, like a lot far more than what you're seeing in clean data.
Mm-hmm. So the maximum, so the ceiling of the data set, basically the observations that had the high value of yield, that decreased a lot from the raw to the clean. That's right. So we decrease here from 4,274 to 2,269. So a difference in the maximum value of about 2,000 units of yield. A lot of difference right there on the max value. Okay, what else? Can somebody else help me with some other observation?
Also, the number of rows changed. Some of them were clean or were deleted on the clean version.
Mm-hmm. So approximately how many rows did we remove?
Around 4,000, 5,000 around.
Around 5,000, right? Mm-hmm.
Yeah.
Nice. How did our mean value change? In what direction did it change?
It's higher.
Higher where? On the clean, right?
Yes.
Yes. So the mean increased what happened with the standard deviation, Kathy?
The standard deviation is reduced in the clean version.
Mm-hmm. And also the CV, right? So the CV perhaps is,
CV is also low.
yeah, so we
Hmm.
went from about 36 to about 26% coefficient of variation. So it's more stable, right? Awesome. So this is basically what happens when we do yield filtering. If we use the yield editor software, it's going to apply all the, if I remember well, 12 filters or 14 filters. So it's going to apply more filters than what we're doing here in R. These are some of the ones that were easier for us to implement in code, and that's why I teach them. But there are some other important filters that are not part of these, right? So there's the delay filter is a really important one. There's other filters as you read the paper. So this is just I wanted to show you how to implement some of those filters in R, and how we can bring in I mean, not all, but some of those filters from a paper and from a software and kind of create our own version of that through programming. Mhm.
Like, if we're using standard for new normalization, is it like more efficient compared to,
So Amandeep is asking if we have multiple sites with yield data, if it's more efficient to do in R or in that. I mean, it would probably be more efficient to do in a programming language, just because you can program all the steps you want to do and all the rules you want to follow. And then you just make a loop and iterate over different fields. So it would be more efficient, but you have to code that, like code that structure, right? Like do a loop and then apply the loop to different sites. Yeah. So actually I had a plan and I still have it. I'm perhaps looking for a specific student to carry this plan, to basically take this class, this script, and incorporate all the other filters on top of it and create a package, like a yield editor package that can be distributed to others. I have started that project, but it wasn't finished yet. And I ran out of my time to do it. So yeah, so basically, my goal was to basically have an R version with all these functions, but of course, when you do a package, all these functions that we're manually coding, they kind of go behind the scenes, right? And you just have one function that says perhaps filter yield, and then everything else happens behind the scenes. The person does not have to do every single step. Yeah, so that's a goal of mine for the near future. All right, so let's look into a density plot. So as we removed a lot of points, we saw on a table format how those statistical metrics changed. So now let's visualize it. I think at least I'm a very visual person. I like to have plots. I prefer plots rather than tables. So that's what I want to do next. So I left you here, the beginning of the code, we have a ggplot and then calling geom density. On the raw yield data, the distribution of yield in pounds per acre, and I'm having a fill of that density as blue and half transparency. So if you run that, this is what you see. Is exactly what you've seen before. This is not new, we're just adding color to it. Now I want to overlay the density of the clean yield data. So, and I want to have a different fill as well. So I want to have a yellow fill. How would you do that? What would you add here?
Let's change the file name to WPF.
So there's one here. So I want to add this on top. So I don't want to replace. So maybe we can go ahead and copy this just to be our starting point. We add a plus at the end, hit return. Let me paste it. So Kathy, you said change the data coming in, right? So we're going to change that to PF, that was our last filter, the position filter. And then what else?
Change the color to yellow.
Right, yep. Perfect. All right, so if we run that, this is what we see. This is the difference. So now we see that the distribution is different. It makes sense, right? Because we remove data points. So now the lower tail is not as heavy. There's not as many, and we can really see that the main effect of the filters that we applied were on low yielding values, right? So on the blue one, which was the raw, there were a lot more low yield values than on the clean version, which is the yellow. So that is what, and then you can really see, which is kind of interesting, that the mean didn't change as much. The mean of both distributions would be the peak of the density. So the mean did not change as much. It's just that the tails are less heavy. We have less data points, both on the lower side especially, but also a lot less data points on the upper side because we cut that right at somewhere here. Right, so this is a visual understanding of this, the statistical distribution of those two data sets. All right, so now we're gonna do so we checked. I want you to notice that we did a lot of things. We checked the results on a table format. We checked the statistical distribution of what we did, and now we're going to check the spatial distribution of what we did. Just as a reminder, yield map underscore raw is an object that we already created. It looks like this. Now my goal is to do the same map, but for the clean version. So I think I left you all the code there, so you don't have to do a lot of coding. But if you just run that, it's gonna make that plot and it's gonna print the plot of the clean yield data. Notice how interesting that is. Right, so if we just compare, right, the clean, or I'm sorry, the raw with the clean, what do you notice? What happened basically? The low yield values are gone, right? So we see these gaps now that before were not there, but we see these gaps where mostly were the low yield data points that now are removed. Not all of them, we still have some low yield data points, but some of them were removed. So remember that this was a wet spot on the field, and these are those gully, eroded sides of the field. Those points were removed. And it's really interesting here because just because a data point is low, like a yield value is low, it does not necessarily mean it's coming from errors. It's coming from machine errors, right? We still have some low points here, right? So we still have, like there's a spot, there's some low yield points here. We still have some of the cells or some of the points that were left around those gullies. So those are still low yield data points, but the really, really low ones were removed. And then there is this question, right? So how do you know if they were truly low values or if they were errors? If we just apply the filter based on speed, then perhaps you can be more certain that the points you're removing are errors, because the speed is the metric you're looking to. You're not really looking to yield. You're looking to the speed. And so if the speed is too low or it's too high, or maybe there's a quick change of speed, then probably that point is an error because of speed. But if you just use the filter on min and max yield, it's harder to say. We may be removing some points that were low yielding that were not erroneous, that they were actually true low yielding points that we just removed because they were too low. For example, what I think could have happened, I don't know, and again, it's hard for us to really know, but I would imagine that low yield data points on this spot are probably truly low because it was a waterlogged part of the field. So plants just did not grow as well, they did not yield as well. However, I would imagine that on the gullies, there is probably a mix, right, between truly low yield points and the fact that the harvester had to slow down and then speed up again when it was going over them. So there is a mix here between perhaps what truly would be low yield points with errors from the combine or from the harvester. It's really hard to know. There is not a really good way for us to separate those effects. So I just wanted you to keep that in mind as you work with yield data, especially this type of spatial yield data, that we want to have a balance because we want to remove what we believe are erroneous data points, but you don't want to remove excessively, especially if are points that are not erroneous. But then again, we don't know what is what, right? It's hard to tell. One point for you to think about is, this will actually be a great exam question. I think I'm not going to ask you in class. I'll hold it for the exam. Yeah, let's do that. Let me actually take note on my notes that you're not seeing. All right. I took note of it on my side, so I'll be asking on an exam near you. Okay. Well, I guess, since I left you on a cliffhanger, does anybody have any questions or maybe thoughts you'd like to share about this? All right. I don't hear anything, so I'm going to keep moving. So I want to show you here a couple ways that we can look into these maps interactively. So one of them here is going to be, let's see, I think I left you all the code. So basically what I'm doing is starting with our clean yield data, piping that into a map view where I'm saying that I want to color the points according to yield. I'm giving a Viridis scale here for it to color with. I'm giving a solid, so I want the points to be fully solid, no transparency. I'm decreasing the point size. I am removing the point outline so that doesn't have an effect on what we're seeing, and then changing the map type to Esri World View. We've done all of these before, so none of this is new to you. I was just walking you through what the code is doing. So if we just run that, and then if we print it, this is what we see. All right, so now, although there is some limitation to how much you can zoom in before the map breaks out, but at least we can have, so right here it breaks out, I cannot really see the base map anymore, but at least we can have some idea of where are those points happening on the field with the base map behind. All right, so as we talked about on these gullies, the eroded parts of this field, a lot of points were removed there, and then remains the discussion of, was that truly low, or was that because of actually errors coming from the speed change when the harvester was going over those? So, all right, now on the next chunk, I want to do some side-by-side comparisons, both static and interactive. So the first one here is going to be, if you remember, yield map raw, I'm just going to print that, was the static map of the raw yield data, and yield map clean was the static version of the clean yield data. I'm using a plus here because that is for the coming from the package Patchwork, which helps us to combine different ggplot graphs. So if you run both of them, you're going to see that output of both maps side by side. So this also helps us to visualize some of these differences, right? So a couple of things to notice is, of course, as you know, we removed a lot of points, so there are some gaps in that map right now. Also, the range of the yield values changed, which impacts the colors in the map, right? So now we see a lot more changes in color on the clean version compared to the raw. And really the raw yield data, we see a lot of like dark colors, not because it is raw in itself, but because he had one observation that was like 4,200 and it's just a single point. So that single point is pulling all this color scale up, right? So you have one single point basically between 4,000 and 3,000, taking all this color space. And then everything else, most of everything else is below 2,000 and lower, right? So there is that skewness on the color scale because one observation is very high and is pulling the color scale with it. That's why on a previous map, we just filtered out everything that was graded, or we only kept everything that was lower than 3,000 because that helped us at least to remove some outliers and be able to see more the color scale patterns on the field, even on the raw version.
It's not that accurate because we all.
Yeah, that's a great point. So Amandeep also made the point here that it could also not be the most accurate map that we could have because we only applied 5 filters. There's still, 7 more that we could have applied. That's also a good point, right? And it's really interesting because, the more filters you apply, the more data you remove. And of course, some of these filters are really important, right? I would say the speed one is really important. There's one that we could have implemented easily with code that I didn't, but maybe if you are excited about coding and you would like to try as a small side project on all the free time I know that you all don't have, you could try to implement a speed change filter. Because right now we're just looking at the speed itself, but we could look into a speed change, which would require a few steps that maybe I did not teach you yet to do, but you would have to basically take the speed of a given point minus the speed of the previous point, and then maybe determine a certain threshold. If that difference is more than, I don't know, half a mile per hour, depending on the direction, if it's positive or negative, meaning it is accelerating or decelerating, then you would consider that perhaps also like a potentially erroneous yield because it is speeding too much or breaking down too much. So maybe that's something that, if somebody is excited about this type of work, you could try on your side. It's not too difficult, but we're not going to do in class. All right, so our next map that I want to do here is going to be a side-by-side raw versus clean yield interactive. So for that, we're going to use a function called sync, which is a function from a package you install on this script here. So the function name is sync from leaf sync package. And we basically need to give it 2 map views that we want to sync and look at them together. So the first one is going to be the raw map view that we already created and already assigned to an object. That object name is yield map. Let's see, yield map raw. Wait, I don't know if I have it. Let me see. This is the clean version. Interesting. I don't know if I have that or if I assigned, but I should have. Let me see. Sorry, let me just check to make sure I'm not forgetting anything. Yeah, this is it. So I was just not looking. I don't think I had this object. Or maybe I did and didn't see. Yeah, I think I did have. All right, well, anyways, this is the object that I was looking for. So yield map raw int. Let me go all the way back again. Right here. So yield map underscore raw underscore int. Yep, that's it. And then you give the other map you want to synchronize, which is the object called yield map underscore clean underscore int for interactive. So the raw and the clean interactive versions. If you run this, it may take just a moment here to work. But basically we have the side-by-side maps on an interactive way. So if you have your cursor on one of them, it should be interesting. It's kind of being hidden behind. I'm not sure why. But you can like zoom in together at the same spots or zoom out and move around. So you can kind of compare like, okay, this spot here. So maybe this is a good point to compare. So this is where we had a lot of low points on the raw and then a lot of remove points on the clean. Maybe let's zoom out here and look for some other regions as well. Oops, it's going a little bit crazy. Notice that, of course, we did this with the intention of doing it, but now there used to be more points on the boundaries, right? So look at like on the red there on the raw, there is a lot of low yield points on the boundary on that last pass, and they're not present anymore on the clean version. And then of course we already talked about this, that near the gullies, we removed a lot of points. So if we come here, for example, and we zoom in on both of them together, we see that we removed a good number of points along the gully that were there on the raw yield version. So this function sync help us to kind of look together at two overlaying plots side by side. All right, so we brought in the raw yield data. We did some, well, let me take a step back actually. I don't know if you remember because it's been maybe a couple classes. But we first brought in the completely raw CSV. And then we did some wrangling on the previous script. So we did, we created that, we turned that into an SF object, we assigned the CRS, we transformed the CRS, and I think we renamed some columns and then exported that. Then we took that SF exported raw yield data and brought into this script and did all the 5 filters, checked for a lot of things. And now the goal is that we export this version that has been wrangled and filtered with 5 filters. We export this to file so we can then use this version in the next exercise, which is going to be interpolation. So just to give you a little bit of a heads up of what's coming up on the next exercise is that we're gonna, because now, well, we would potentially need to do interpolation even on the raw data, because as you realized, even though on the static map it looks continuous, but it's not, right? Those are points. So if you zoom enough, you see the gaps. We would still need to interpolate so we have a continuous map of yield data everywhere and not just points. So even if we had not cleaned, we would still need to interpolate. In our case that we did the cleaning, besides just having space between points, now we have these larger areas of empty yield data that are the points that we removed. So now the next step we're going to do next class is going to be to interpolate our wrangled and clean version. Because we want to reutilize this data set that we developed today, next class, we're going to export this object to file so we can easily just import it back into the next script. So we don't have to have one script that does everything, right? So we can break down our flow into different scripts. So imagine that you have raw data coming in, a lot of things happen with that data in the script, and then in the end, you have a product that goes out. And that product that goes out then becomes the new data frame coming into the next stage. That's what we're doing here. All right, so with that, let's export to file this, this clean version. I'm gonna leave it completely to you to tell me what to do here. I think you've been doing this enough already, so I'm gonna rely completely on your advice. How would you export? So what function would you use? And what object do we want to export here? So let me ask Benedetta, what function would you use here to export the clean yield version? The data sets, yes, right? SF. Well, sorry, can you repeat that? I was speaking as well.
Write CSV for the data set.
Okay, so right, but do we want CSV or SF?
CSV,
Why? Why do you think it's CSV?
because we want the data set, you said.
Okay, yeah, so maybe I confused you, but so I really want to export the yield clean data, the clean yield data, right? And right now that clean yield data is an SF object, which is a vector geospatial type. I want to keep that. So we could export the CSV if we wanted. There's nothing wrong with that. But I do want to keep the spatial information about those yield data points. So because of that, we're going to do a write SF. But it could be write CSV if we did not care about the spatial component. All right, so write SF. What is the object name that we want to export?
Is the sync yield map. Do we want the both of them or just the last one, the clean one?
So we just want the clean one.
Then yield the map clean int.
Okay, so that's a tricky question from my side because this is a map view object. This is not the data sets. This is not a data frame. So if we just print yield clean int, this is a map view object of the clean yield data. So it would not be this. I mean, it is a similarly, the name of the object I'm looking for is similar, but it's not this. Let's see. Polly, what? Sorry, Benedetta, go ahead.
Yield map clean.
So it would be the yield W17 PF, right? That's the last version that, even though we created this object a good number of chunks above, but that is the one that we want to export. Perfect. All right, so now let's give the path here. I want to get outside of code, inside of data. I want to name this, and please name similarly to me, because otherwise you're gonna get lost in the assignment. I want to name this yield 17 underscore clean dot geojson. And then finally, we want to have the argument always here, delete underscore DSN equals true. So just a quick comment here, so at some point we're going to start talking about our midterm, which is going to happen. I think it's going to be on the 27th of February. So in a couple of weeks, we're going to have the midterm. And we're going to talk more about that in the next class period, maybe. But something I want you to keep in mind is these things that we're always doing. We're always using the same function. We're always using the same things. And I'm always telling you, this is important. This is what we do. Especially if I ask you, what function comes here? What argument we change? Those things I'm only asking you because I think they're important for you to be thinking as well. So every time I ask you something like that, there's a good chance it may be on your exam. I'm not going to be asking you like things that we use once, like a function that we saw one time. That's not the type of question I do. I'm going to ask you things that we use almost every single exercise. Those things is good for you all to be thinking about. And if something is not clear, why we're using something, why we're changing an argument, then ask me questions, or maybe, look at the documentation of the function, but study those things because that's what I like to ask on exams.
But do we need to know the code by heart?
No. So, so again, I may ask you, for example, what is the function you would use to export an SF object? Or maybe I will show you a data frame that could be an SF object or not. And I'll tell you what function would you use to read this object. Things like that show me that you're understanding these relationships and that you're following along in class as well, right? So, but I would not ask you to write by hand code. Just max I'll ask about that is the function names. Like what is a function that we've used a lot of times to do this task? That's something that's fair game. All right, so make sure you do run this chunk here because we want to have this data set exported. If you run that, you come on your Files tab. We exported to data, so we should be under the data folder. You should have there the EO17 clean.geojson. All right, so if you remember, the processed is what we called after we wrangled, and then we brought that processed, and now we cleaned, and now we export the clean version as clean. Okay, so save your script. A quick summary about today is that we learned how to implement 5 filters of the yield editor software that were based on the min and max yield, min and max speed, and position. And then we compare the raw and the clean yield version to see what happened with the statistics, what points were removed, what parts of the field are those removed points coming from, right? So really creating an understanding of the data as well. Okay, so we have here 9 minutes. We're not going to start a new exercise. I just want to give a quick moment if you have questions about what we just did. If you do, we can cover that. And then after that, I just want to talk to you a little bit about the assignment 5. So any questions about what we've done until now?
My question is about the midterm. Can you give us like a heads up, like the structure of how the midterm for this course is structured? Maybe if it's a multiple choice, if it's a text or paragraph, how is it?
Yeah, so it's going to be a mix. It's going to be a little bit of everything. It's going to have mix and match. It's going to have multiple choice, select all that are correct, short answer essays. All those things are fair game. It will not be in R. Yeah, it's going to be on ELC. So you're not going to have to code, but you're going to have to know about these functions that we're using a lot. So if you want to, I mean, we can talk more about this in the next couple classes, but like, you know, if we had a lecture, go through the lectures. If we had a reading material, you know, make sure you read the material and you understood what was it about, what it was about, like the paper, for example. What else? All these functions, if you study the scripts, it's themselves. Of course, I don't want you to be remembering 1,000 functions. That's not the goal. You will never do that, even if you're programming, even if you have a computer in front of you, you wouldn't remember them by head. But there's maybe 5 to 10 functions that we use almost every single exercise. Those you should be familiar with their name, what they do, and some of the most important arguments that we've been using in class, right? I'm not gonna ask you like, you know, let's say the function write_sf. If I just ask for the help of this function, I'm sure it has a ton of arguments. If we just quickly check on that. Right, so it has like DSN, layer, driver. I would never ask you something that we have not used in class a lot, right? That's not the type of test I write. So just make sure you understand what we're doing, you understand what the chunks that we're doing, that we're coding are doing, and create that understanding. And you should be all right. Okay, so we have just a handful more minutes. Make sure you save your script and you can close here if you want. I pushed to GitHub a few files that are related to this assignment. And I do want to give you a heads up. We're going to get to a point of the course where, unfortunately, it's the nature of it. You're going to have limited time to turn in your assignments. The reason for that is we're going to be doing in class analysis for 1 year. And then I'm giving you 2 other years on your side for the assignment, for the same field, but 2 different years. And I'm basically asking you to repeat what we did for 1 year, repeat that for the other 2 years on your side as an assignment. And the reason why you're not going to have a lot of time to do it is because each of us are gonna have to have the final products of all those 3 years for the next class period to move on. So you kind of have to do the assignment maybe in 1 or 2 days. It's not super difficult. We're just gonna mostly be copying and pasting the same code and just adapting. So it's not like I'm asking you to create a whole script out of nothing. But it may be challenging because you're not gonna have a lot of time. And for you to be able to then follow up in class, you will have to have done those processing steps on your side as part of the assignment. Because I'm not gonna share with you. I share with you the raw data of the 2 new years. I'm not gonna be sharing with you the intermediate steps for those years. That's something you create on your side. So this one here is not as bad because I think you have until Monday, 11:59 p.m. to turn in. But if you go to our GitHub repo, if you download the version of the newest GitHub repo, you're gonna see a few files, well, maybe a handful of files. One of them is under 02 assignments. There's gonna be an assignment 05 yield editor. There's a Quarto file in there. I'm just gonna launch the Quarto file so we can go through the instructions very quickly. But basically, what I'm asking you to do is to do both the wrangling that we did on the previous script and the yield monitor data cleaning for 2 new fields. In class, we did for 2 new years of the same field, I should say. In class, we did all that for 2017. I'm asking you to do all those steps now for the same field, yield data from 2019 and 2020. For that, on the GitHub page, inside the folder 03 data, there are 2 new CSV files, yield 19 and yield 20 for those specific years. I want you to copy these 2 new data sets into the data folder of your 07 yield monitor. So you're basically going to be using the same R project that you used for the in-class exercise, but now with the files for the assignment. So move those 2 CSV files into the data folder of your 07 yield monitor. And so as part of the assignment, you have to wrangle the 2 data sets and clean them, and then provide me with statistical summary of the clean version, which are the questions below here. So I have 2 questions. So notice that I'm not asking you to send me the data set. I don't want you to send me the GeoJSONs. What I want you to do is send me this Quarto file with the instructions, just with a table, a summary. It can either be in table format or you can just write here, like min was whatever, max is whatever works for you. You may write in words, or you may bring in the summary and provide me a table. But I want you to tell me the minimum, the mean, the max, and the CV for the clean yield data for 2019 and the clean yield data for 2020. This is what I want from you. On your side, to give me those answers, you're gonna have to create the process version of each one of the years and the clean version of each one of the years. So you need that on your side. Make sure you are exporting those files on your side. But then to answer me, I just wanted to give me a summary based on those files. And then, as always, you render this as HTML and submit on ELC by Monday, 11:59 p.m. I have more instructions here, like move this script A5 questions into your code folder of the 07 yield editor project. And then move the data sets that I pasted on 03 data as well. So that is your assignment. I know we're getting to the hour here, so I want to take your attendance first. You can claim your attendance. And then if you want to leave, you can leave. And if you have some questions, I can stick around for a moment. All right, so make sure you claim your attendance. The issue has been opened. And then if you have any questions, let me know.